Perfect. Thank you very much, Christoph. And hello, everybody. So my name is Leonhard Schreiner. I'm a PhD student at g.tec, and I'm working mainly with the g.Pangolin system. And I'm giving a talk today about the research we do with the system here at g.tec in Heidelberg. The agenda for my talk is first, I will give an introduction to high density EEG in general. Afterwards, I will proceed to explain the g.Pangolin system, the technical background, how the system works. And then I will show you how we set up our experiments and how we conducted them using the ultra high density EEG system. And in the end, I will show you the results of our scientific studies, which are mainly clustered in motor decoding and visual decoding. As a short introduction, I guess all of you already heard it throughout the day about electroencephalography EEG and brain-computer interfaces. So what we are focusing on with our ultra-high-density EEG system is non-invasive on the scalp with a very high electrode density. So EEG is widely used and offers a high temporal resolution. It's fast set up, but sometimes still lacks in the spatial resolution. And the BCI is, as Walpole defines it, a system for controlling a device, a computer, wheelchair, or prosthesis by human intention, which does not depend on the brain's normal output pathways of peripheral nerves and muscle. And that's also how we use the g.Pangolin system. About high density EEG, you can see here on this slide state-of-the-art high-density EEG systems. So you can see the sensor positions, how they're located on the scalp, and typically they're still attached like a standard EEG cap with the electrodes, silver chloride often, with saline solution or with gel for a better impedance. And that's still the state of the art in high density EEG. So what means high density? It means like basically that you have a higher channel count. So compared to standard EEG systems from 32 to 64 channels, you go up to 1000 channels as we can achieve it with our g.Pangolin system. So this higher spatial resolution delivers you the opportunity to capture neural activity more precisely. You also, as literature shows, can do better source localization because a high electro count is very important in that field. And there are a lot of possible applications, as you just heard from the presentation before. And there are also some challenges that we need to overcome. So we have a lot of data because we have a lot of high spatial sampling and also temporal sampling, which makes processing complicated, and also the setup of the system itself can be longer. The motivation behind the work is based on a couple of topics. So it is shown in clinical research that especially for localizing epileptogenic sources, the improvement is very big when increasing the sensor density. So for example, one study that I mentioned here compared a 128 to 256 channel setup to a 32 standard EEG setup, and they had way higher sensitivity and specificity with localizing the epileptogenic sources. With that, the high density EEG is needed to avoid the spatializing to not have mislocalizations. Also in visual decoding, there is some studies that present that you can get better decoding performances. And this is also something that I will show you today, how we did it with our studies. And additionally, the publication count for high density is increasing very much in the recent years. So I have here the figure on the right side from 1980 to 2025. We have a big slope here increasing and in high density EEG. So this is for the motivation on the work with high density EEG. And now here you can see the setup of the g.Pangolin system that I'm going to explain you in detail compared to standard EEG systems. So what you can see here is on the left side, the standard EEG layout with the dark gray circles, so the 1020 system. And with the light gray filled circle, we have the 1010 system. And the empty circles are the extended 1010 system, which is also visible on the right top with our standard wet active electrodes here, the Scarabeo electrodes on a standard cap. So this would be the electrode count, and also similarly the electrode diameter, for example, so the exposed sensor diameter of a standard EEG electrode is approximately 10 to 15 millimeter. Of course, if you add gel, this can vary, and this also makes it unstable diameter. And if you put our g.Pangolin electrode grids on top of this standard layout, you can cover with 64 of those grids that you can also see in my screen now. So they're basically flexible PCBs that are attached to the skin. And here we have 16 electrodes on one grid. And if you take 64 of those grids, you can cover with 1024 channel here the whole scalp. And in the center figure, I made a comparison of the electrode size also of our g.Pangolin grids compared to the standard size. So you see here, for example, around C3, you would have one electrode is covering roughly what 6 g.Pangolin electrodes covers of the area. And we have here 16 grids. So this is also on the right bottom, you can see when the preamplifiers are attached to the system that I will explain you in a second. So here are the capabilities of 1024 channels using the system. And the grid looks like so, as I showed you before in the video. We have 16 electrodes on one flexible PCB. These are gold-plated electrodes, and we have a preamplifier, so we get a good signal-to-noise ratio and a good stable connection. And we attach the PCBs with adhesives to the skin with those resections, and we fill the resections with conductive gel. And by that, we make sure that there is no shortcut in between electrode positions, which is very important when doing high density EEG. And this could also be something that other systems lack in because they have to place sensors very close. So the risk that, for example, saline solution or standard applied gel makes bridges is very high. And in our case, this risk is not given because we have here these resections and every electrode is attached on its own space, and it's also not moving because, as you can see here on the very left side, you have to attach it to the skin. And that's why if you want to use it in EEG, you also need to shave hair. For example, in EMG or behind the ear, you can also use it here. And in that case, you attach the grid and then attach the preamplifier, and you can use the system. This is for one grid. And if you want to use more grids, the geometry also delivers a good opportunity because the g.Pangolin system is called the Pangolin because it has this pangolin scales-like shape, which covers very nicely spheric surfaces. So it bends very nicely to the shape of the head, for example, or to other shapes of muscles, anatomical shapes. So, and also if you use more grids aligned next to each other, you have always the same inter-electrode distance. So if you attach grid by grid, you keep the same distance and you can extend the amount of channels that you want to use depending on your experiment and setup. And here's a schematic overview how we integrate the system in our standard biosignal amplifier setup with a G.High amp. The G.High amp offers sampling of 256 channels with very high sampling rates, and we use this to interface our g.Pangolin grids. So we have a connector box that makes it possible to merge 16 preamplifiers with each 16 channels, which means we have 256 channels per connector box. And then we can use more high amps simultaneously with our software, so we can merge several connector boxes, so we reach even a higher channel count. The grid itself has a sensor distance or inter-electrode distance of 8.6 millimeters, and the diameter is 5.9 millimeters. And on the left side, you can see the grid in C attached to the skin, and then the preamplifier attached on top. The cables that we use are very slim connector cables for the preamplifier. They need to be very light and very slim, so they can be used nicely without a lot of cable movements, and also without too much weight on the head of the subject, because obviously if you have so many channels, even the weight of the cables is impacting. So as I said, each grid has 16 channels, which are gold electrodes, and we power the connector box with a battery pack, and we use a ground electrode with standard disposable adhesives. Normally we use it, so for my studies, we used it at the mastoid basically, but you can place the ground on other locations as well. For example, if you want to measure EMG or ECG, which the system can also be applied for. And here you can see how we approach the experiments typically using the g.Pangolin system. So the first step is that you build a 3D brain model with the sensor grids applied in the software on the locations where you are interested in investigating neural activity. For example, you would go here for auditory on the temporal lobe, for visual, as we did it here in occipital, and also we used it for motor decoding over the central sulcus, the somatosensory cortex. So this depends a lot on your experiment, or you do a full scalp coverage, which is also possible, of course. And after preparing this electrode layout and the montage according to your planned experiments, you place the grids. And of course, you need a reference position, because you can place the grids on any position where you want. So what we did is mark standard position like the vertex, and then place the first grid here, and alongside we move forward with the other grids. And with that, we keep the inter-electrode distance, as you see, and it also fits then in our brain model. So we got the MRI of each of our participants, and with that we can do source reconstruction and also do this placement of electrode grids in the software. So if we then prepared all the setup, the layout, the montage for our measurement, we attach the preamplifiers, we plug in the biosignal amplifier, and we can start up the software. First steps are always checking the EEG signal quality, and then do the first experiments. Experimental setups are very typically like in EEG. We have a screen, we have some objects with interacting. So that's how we set up the experiments. And in the fifth step, we do the data analysis offline, or meanwhile doing the experiment online. So we can calculate a classifier, do real-time BCI experiments. That's the typical approach for data analysis. What we often focus on, particularly with the high density interesting, are topographies. So here the surface activation maps are very interesting. For example, here for a visual evoked potential, you can see clearly here on the occipital lobe, here on the occipital pole, the first income of the activation at 0.1 seconds, so it's the N100. And here are all the channels, in this case, from around 400 channels color-coded, which channel has which activation. And we have here -2 + 6 microvolt activation, and we have here is N100. Then we also, for decoding purposes, see accuracies over time, and also compare with standard EEG layouts if we can see some improvements. And for the co-registration, something important to mention is what we did for the studies. There are different possibilities what you can do. For our studies, we used markers in the MRI and located them on the standard EEG positions. So we could afterwards find it in our software. And with that, we could then place our grids in the 3D montage editor. And you can also use, for example, 3D coordinate estimation software like Polemos to find the sensor positions in real world. And here you can see a short video how the grids and the attachment looks in real life. So you can see here for one of the first studies, we located it very central, 256 channels. Here we have the application of the electrode gel, and we attach the preamplifiers, as you can see here, and we perform different experiments. And yeah, this is the standard setup. We check in the software the signal quality. We have here also the 3D brain models that we can also use in our software for real-time investigation of the data. And here an example, 1 to 228 channels from the Pangolin. This shows you already, you have a lot of data, especially if you work with more than 500 channels up to 1,000. Compared to a standard EEG experiment. Yeah, there is a lot of data coming in. And also the main research questions that we ask us is, what is actually the impact of the sensor area, the inter-electrode distance, and the electrode density on the decoding accuracy, spatial resolution, and the source localization of the ultra-high density EEG systems? And another research question is, which advancements do the ultra-high density EEG systems provide in decoding motor and visual neural activation by performing source localization, and also serving as a hybrid system for using it EEG and EMG for advanced applications. And as I mentioned before already, the main topic were motor decoding and also visual perception and visual decoding in the second main topic that I will show you now, the studies that we did. A little introduction for motor decoding. Here you can see the homunculus with the somatosensory and the motor cortex divided by the central sulcus. As you probably all know here, the representation of the different motor areas. This is also particularly important for all of the studies that we performed. The first study I want to show you is we did decoding of hand gestures using our g.Pangolin system. For this study, we applied the pangolin sensor grids on the scalp contralateral to the moving hand, and we had 3 hand gestures that were performed. Fist, full finger extension, and extension of the index and middle finger. You could also call it a rock, paper, scissors experiment because it's the hand gestures of this game. And we randomized, we shuffled them. We asked the subject to perform them for 1 second. We had interleaved resting periods. And then we did topography plots for results, and also we calculated the accuracies for the different hand gestures. On the left side, you can see the setup. So for this study, for example, we used, depending also on the anatomy of the subject, up to 400 channels centrally on and contralateral placed. And for that, we needed 2 G-high amplifiers that we could synchronously acquire the data from. And in the bottom here, on the bottom right, you see the topographies. So we did motor execution for subject 1 and motor imagery for subject 2. And you can clearly see here the different gestures with the different activation maps, more pronounced for the motor execution, in this case for subject 1, but also for subject 2, the motor imagery, we could achieve nice activation maps with also accuracies up to 75%. In this case, I have a plot of rock versus scissor hand gestures for the motor execution, with the accuracy peaking around 1 second after movement instruction, and then going down again, and it's coming from here from chance level 50% of the 2-class problem. This was the first study we did for decoding motor movements. The second study I will present to you now is using the system hybrid. So we used it for EMG and EEG at the same time. And with that, we wanted to map the representation of grasping movements. And on the right bottom, you can already see schematically how the setup looked. So we had different objects, which you can see here on this slide. We had the sphere and the cylinder object and different grasps. So we had a power, a precision, and a pinch grasp. And with that, we had a lot of different classes, and we used EEG features. So in this case, motor-related features from 8 to 30 Hertz, band power, and EMG features, RMS features. We used EMG features in a range of from 20 to 200 Hertz. And we then did classification, and we plotted the activation maps. And you will see in the next slide here different accuracies for EMG and EEG. We did this for a total of 12 grasping conditions. And on this slide, you can see here the main results of the study, which are on top, the event-related desynchronization and synchronization maps. So you can see the MRI head here with the activation maps from second -1, so 1 second before the instruction of movement, until second 4, the movement instruction was giving. And then you still can see here the plots until second 8. So we also want to investigate what's happening in the period after the instruction. On the second row, you can see the EMG activation plot as intrinsic and extrinsic, meaning the muscles on the forearm and the muscles on the hand, the extrinsic. So we here plot the different like maximum voluntary contraction calculated in percentage. So what we did to get the maximum voluntary contraction, we used a dynamometer and asked the participant to press as strong as they can. From that, we used the EMG activation to calculate the 100%, and of that we then calculated from the activation happening in the experiment the percentage here for the EMG activation. As the ground truth, we also made a video by detecting the movements. So we can hear a video of the hand itself, and we had like this hand tracker. So we see the hand velocity of the hand rising up with a short delay after the onset of the instruction, and then going down. So the subject were lifting their hand, going through to the object, and then after the instruction ended, they were lifting it up and going back again. This is what you can see here with the hand velocity. And additionally, we did classification of EEG and EMG. And here in orange, we see the EEG accuracy and the chance level in slashed. And we can see the EMG accuracy here in blue and the EEG in orange. Obviously, the EMG is reaching a higher peaks. On the right side, you see here the 100%. So we reach around 95% and a very stable plateau of accuracy. That's something we can definitely say that the Pangolin using it with EMG gives you a very good distinction of also fine-grained movement, just finger movements, gestures, grasping. So very useful in this case. And additionally, we investigated the 2-class problem of the EEG here in this case. So we can see an increase in accuracy similar to the study before, after 1 second, 1.5, we reach a peak of almost 80%. It goes down a bit, and then towards the end, for the movement intent of lifting it back, we have another increase in accuracy, which goes down. And on the topographies, we can see here ERS at the end of the movement, and particularly strong activation again, where also the accuracy is peaking. The takeaway from the study is that we can have clear topographies, which show very interesting also the focal spots, where here the movement intent is happening. And we have a fast activation in extrinsic muscles at the movement start, and sustained activation in intrinsic muscles during the grasping. And there is some temporal delay between the muscle activation and the detected movement. So this is what are the main findings from the study. And the next study that I'm going to show you also in the motor decoding section is the first study we used the ultra high density EEG system for source reconstruction. So what we did here is vibrotactile stimulation of all 5 fingers, and we recorded the g.Pangolin EEG here again centrally located 256 channels with our g-high amp, and then we used the somatosensory evoked potentials by the vibrostims to perform source reconstruction, also plot these EPs here for the different fingers, as you can see. So very important in this case is also that we have a precise timing of the activation. So for plotting those evoked potentials, it's very important to have a hardware trigger. So we feed back the activation of the motors for our vibrostimulation. So for these vibrotactile stimulators into the g.high amp with TTL trigger, and with that we have it in the data, and then can perform plotting of the evoked potentials for the different fingers. Here the average for all fingers, and with that we can then solve the inverse problem. In this case, we use the field trip toolbox here with M&E and the dipole fit approach. And so you can see clearly the spot on the contralateral side, because we stimulated here on the right side, and also different spots here for different finger stimulations. And I superimposed, I put all the dipoles from the source reconstruction here in one slide. So we have a right hand finger stimulation on the left bottom figure and the left hand finger stimulation on the right bottom figure. And you can see here in the different colors the different finger dipoles that are very close to each other, obviously, but we can find here differences in localizing the sources, which showed us very nicely that we can use a lot of channels, and it seems to be beneficial also for source reconstruction. Another big study that we did is decoding individual finger movements. Similarly to the plots before, we focus on topographies and accuracies for decoding purposes. We measured in this case 5 subjects, and you can see here in the center top how the setup was looking. We had actually an avatar that showed which movement needs to be performed, and you see the grids attached. On the back side, you can see the g.Pangolin system and the g.high amp, and we recorded individual finger movements. And you can see here the setup of the activation starts again after 0.5 seconds and lasts until 2 seconds here. And we can see here the so we can see here the accuracies is peaking similarly at 1.5 seconds after the movement. So the avatar showing the movement to be performed. And on the right top, you can see very nicely the representation of for each channel, we did the representation of each finger. So we investigated the significance for each finger on the channels, and you can see clearly a focal spot here inside of the contralateral placed electrodes here with different colors coded for the individual fingers. And you can see here the time frequency maps, also ERD happening here in the mu and beta band, and then the ERS in the beta band here for all the different fingers. We could find 70.6 accuracy averaged for here the finger decoding. And again, we investigated here a subset. So this was actually the first time we did a subset analysis. We selected subsets of electrodes and wanted to see how the accuracy changes. We used the standard 1010, the extended 1010, and the ultra high density EEG electrode setup, and we calculated the mean accuracies, and you can see here an increase in 12% for the finger decoding. And we also checked if we have here like the correlation of the electrodes. So we checked if there is more information in like smaller distance, and that's what we could also find, because even if the with the correlation different we see here that even if the distance gets very small, we also have a gain in information still that we can have from the system. We used here the Pearson's correlation coefficient. And another study that we did is a direct comparison between the ultra high density EEG system and the standard 1010 EEG. So we used the two different systems. I'm just here showing the electrode layout. The subsample analysis I showed before was using it from the same measurement, but just single electrodes as subsamples representative. In this case, we used just two different systems. And you can see here, we have in a similar region 73 channels actually for the ultra high density EEG and just 9 for the 1010 system. You can see it here again also. And again, we checked significant channels for the finger movement, and you can see here these focal plots for the ultra high density EEG system and very widespread activation here for the standard EEG system that we could also find in our results then, because we saw that the single finger activation here is different between here the ultra high density EEG and the standard EEG, and we have more information here in our focal spot because more standard EEG channels are active with each finger in the standard measurements. And here again, we plot superimposed the most significant fingers here for each channel, and we can find again this focal spot here overlaid on the standard EEG system. So you can see just the surface of a couple of significant electrodes we have here would be, let's say, 2 standard EEG electrodes. So that's something that you couldn't differentiate as good as we can do it with the system. The last study here I want to mention about the motor decoding is here actually a mapping study. So we tried to map the central sulcus by performing median nerve stimulation. So we did a stimulation on the median nerve on the forearm, and we recorded the somatosensory evoked potentials from the sensory and motor cortex. Here you can see typically we have a N20 and a P30 in the sensory area on the central sulcus, lower activation and also different temporal behavior. And then we have this phase inversion in the motor region. We have a P20 and a N30 typically, and we used here again 256 channels overlaid so we could cover as good as possible here the left and right hemisphere, the central sulcus. And on the right side, you can see an example plot of 10 channels selected across the central sulcus. And you can clearly see here the inversion of this, the phase reversal of the somatosensory evoked potential with the N20 and the P20, and when it goes toward the central sulcus, we have here less activation, and we have this reversal that we also showed for all 5 subjects in this case, with slightly different timing. And we use that with different approaches here to map the central sulcus. So we used a peak detection method and a spectral clustering to delineate here the pre- and post-central area of the central sulcus using the inversion of this phase, and we could delineate it quite nicely with an accuracy of 95%. Using here the spectral clustering method that is also used in invasive data, so with ECOG data, achieves similar here results. Of course, limitations of this study would be to perform a source reconstruction here for a precise mapping procedure. And as the last topic, I also want to show you some results from our visual decoding studies that we performed. So also here a little introduction, general, how the visual impact evokes here potentials in the occipital lobe. We have here the primary visual cortex, where we can find the earliest components in the visually evoked potentials, and then we have the dorsal and the ventral stream, which the ventral stream is typically handled like the what path, so what is to be seen, and the where and how path here, the dorsal stream. And for the first study, we tried to decode here different color stimuli by placing the g.Pangolin system on the occipital region. So we placed here 500 channels. So we used 2 full G-high amp amplifiers, 512 channels, and we showed different colored grating stims. You can see here the different topographies. And again, on this occipital pole, the activation for the different colors, and in minus and plus 6 microvolts. And from that, we plot the visually evoked potentials, and we calculated again the accuracies. So we can see, of course, the more trials you average from the visually evoked potentials, the higher the accuracy rises. So with a 10 trial average, we can reach actually for one subject 100%, and the others have a bit lower accuracies. But even with, so we have here, I'm talking about the 4-class problem actually, even with just one, so single trial stimulation classification, we have here 70% for subject 1. And similarly, we select here on the top right the time point for the highest accuracy. It could differ a bit between subject in this case. And one last study I want to show you, the most recent one that we did is showing here the visually evoked potentials and the impact in decoding different visual properties, and also using it for source localization. So similarly, we placed 512 channels here in this occipital region. We showed stimuli, in this case, body, pattern, objects, and faces. And we recorded the data here with 2 high amps. And this is, for example, compared to the standard layout system, the g.Pangolin electrodes placed. And again, we did a subsample analysis. So just for an explanation, we used single electrodes of the g.Pangolin system and compared it to the performance of the full layout. So the subsample of the 1010 is here marked in red dots, the extended 1010, for example, red and blue, and even denser than, for example, the 10.5 system that we also compared. We also used again here the MRIs of the subject, especially because we wanted to perform the source reconstruction. For signal processing, we had a lot of different steps. So we have some initial processing by just identifying bad channels, removing them, and afterwards performing a common average reference. That is actually typically what we do with our high density data. And then we process the data with a bandpass, we epoch them, we do some baseline correction, then we plot the visually evoked potentials. And from that, we also plot the topographies afterwards, we perform classification here, for example, with the temporal generalization method. And additionally, another path of signal processing, we did the source localization. Here, using our anatomical data, computing the forward solution, and then visualizing the inverse solution of the activation. We used in this case for source localization Python MNE and the S-Loretta algorithm. And all of our classification, also of the results that I will show you, are 4-class problem, single trial stimulation. So this is actually the main results showed in short. So we have here the activation shown from the Pangolin system on top. For the phase stimulus for subject S1 in this case, we can see here, for example, at the early N100, you can see it here on the occipital pole, similar to the plots that you have seen before already. And this then proceeds, goes more lateral here on this side, on the temporal region. And you can see here some activation here also in the ventral plot, here in this fusiform gyrus, which we could find with the source localization here compared to the standard Pangolin plots. We get very important insights in that case with all the electrodes that we use. And as another sub-analysis, we wanted to know what is actually the difference in impact of sensor density and actually the sensor area. So of course we know that our Pangolin electrodes have less exposed sensor area compared to standard EEG electrodes, and wanted to see what impacts the performance more here, increasing density or just increasing the area. And you can see here on the right plot that here are some example head plots marked in different steps of sensor distance. So we have here from 40 millimeter high distance to 8.6, which is our g.Pangolin distance. And on the bottom x-axis, you can see the coverage area, which is from low to high in that case. So we increased here the coverage area, and the different head plots represent the different distances and coverage area here in this figure. We mark specifically here the 1010 EEG system. So if you here merge all of those electrode surfaces, you would reach a similar setup than with the star. And with that, we calculated for all 4 subjects the accuracies in our 4-class problem. And we could then fit the curves. And we saw that with increasing the area, you get lower increase in accuracy than with increasing here the distance. So the blue dots, for example, are here the standard 1010 system of the electrodes here. And you can see here in the last white filled circle, this is the ultra high density setup. So the full count of electrodes. With that, we reach the highest accuracy, and compared the star is here the 1010 system with low accuracy. Here in this case for visual decoding for the 4-class problem. And temporally seen, we also did some investigations and saw that there is a clear behavior. So you can see here this temporal generalization maps, and you can see a clear increase in accuracy at the N100, and then a little dip, and again around 200 milliseconds with the second phase of the visually evoked potentials, slightly different for subjects. And particularly interesting was also we plot this for our electrode subsets, and we somehow expected lower accuracy peaking, and that we also can see here with the lowest of the 1020 system electrodes and the highest the ultra high density. But what we also saw is actually a different temporal behavior. So we have a faster increase, a faster onset of accuracy using higher density electrode system than lower density electrode. So here the spatial resolution of the EEG electrodes also gives us improvements in temporal resolution of decoding. And again, as a comparison, we did here some plots with the subsets, so the 1020, the 1010, extended 1010, the 10.5, and our system. And with the subsets, we then performed plots with a similar interpolation method. And you can clearly see that the 1020 system electrodes selected do not evenly here give us the nice activation maps that we would expect. And the higher the density goes, the more clear are here the borders of the actual activation. And similarly for source localization, we found stronger activation with higher sensor counts and also more here focal spots compared to lower densities, which shows us the improvement that we can gain with the system. And again, here we did accuracy plots, accuracy calculations here in the 4-class problem. And similarly, we achieved an improvement of the accuracy compared to also the motor decoding studies where we saw a similar behavior. And yeah, one last analysis that we did is also averaging electrodes, because of course with averaging electrodes you get a higher signal to noise ratio. And we saw that also not just using independent electrodes, but averaging a high amount of electrodes already increases the accuracy very much, starting from using like all the electrodes on one grid, averaging them to here like 4 groups of 4. We already achieve a big steepened accuracy increase, and can see that also this averaging behavior gives us good improvements in decoding performance. And in the end, I just want to answer the main questions. So particularly important, which advancements our system gives us are the focal source plots in the motor and as well in the visual decoding experiments. We have a more refined source localization, and we achieve higher decoding accuracies compared to the current methods, and the technology is very scalable. These are the main benefits here in this case. Also, it can be applied for real-time BCI applications with avatar feedback. For example, we did a study with the hand gestures, and again, also for creative applications. For example, we did here the Pangolin Scales project, where we interacted here this LED and motor animatronic dress with our BCI system. And the outlook would be definitely coming away also from a lot of cables, going in wireless technologies, and translate the research to clinical, especially when it comes to epilepsy, to go here in the clinical area. And here are the references, and I'm very welcome to answer questions, and thank you very much.
Thank you very much for the nice presentation. The first one is the material. So is that the polymer that you used for making the grids, or what is it?
So for the grids itself, it's basically like flexible PCB. It's polyimide with gold electrode. So it's a very simple PCB that is very flexible. Actually, in this case, I will show you again here in the camera. You can see how much I can bend it. So you can imagine how good it can attach to, for example, the forearm or the surface of the scalp here. So yeah, flex PCB in that case.
Maybe you can close the screen sharing, because then the video is bigger and we see it better. So what's actually the dimension and the thickness of the Pangolin grid?
So the width is 35 millimeters and the height is 55. And we have a sensor diameter of 8.6 millimeters and a sensor distance of 8.6 millimeters and a diameter of 5.9. The thickness is very slim. It's actually 0.1 millimeters. So it's very slim, very bendable. So also very good to be attached to the complicated geometry of our body, obviously. So that's very important that it's super flexible, and also the geometry. If you can see the slits specifically, that's why it's also called the scales, the pangolin scales. They can bend particularly good, and also with that you have way more possibilities to attach than, for example, with a square grid.
Is there any allergic reaction on the scalp, or is there anybody who should not use it?
No, so for now we don't have any allergic reactions. Of course, it depends on the materials of the medical adhesives and the gel, but they are both medical materials. So the EEG gel and also these adhesives are to be used with skin. Of course, you always need to take care when preparing the skin, because we suggest to clean the skin. Of course, you should shave before when you do the EEG measurement. So if this is handled correctly and cleaned nicely, everything is going fine.
Colin is asking, does a subject have to shave the hair to have such a robust system of electrodes work, or would a wet gel placement of electrodes be sufficient?
So in our case, we definitely suggest to shave, or at least have it shaved like the last 2 days, because then the attachment and also you have a way better contact of the gel to the skin, and with that also no bridges. And this is also the main benefit of the system, I would say, because if you have hair and use high density, the risk of having bridges or a different contact area of gel is also very high. So we definitely want to use it in that way, because this also gives us the benefit.
And it's not difficult to find subjects who want to do it. So many applicants actually mention, I would like to shave my head to use the Pangolin. Can I come? Another question is gesture classification. Which signal features did you actually extract?
So for our EEG features, we used the band power features in the alpha and beta band here in this case. And for the EMG, we used very simple root mean square in the 20 to 200 hertz frequency band. We can record very nicely simultaneously EEG, EMG. Afterwards, in the processing step, you just process it differently, but of course you set the sample rate accordingly. So it's accordingly for both modalities. And then in the post-processing, you just handle it accordingly.
Sonic is asking, is there any signal interference between all these closely placed electrodes with the Pangolin system?
As I mentioned before, so we don't have any shortcuts because of the main setup, or like this, like the resections in the grids. And we also checked here the correlation, as I showed in this one plot. So the correlation, of course, increases with smaller density, but we still gain information. So it doesn't increase linearly like the density. So we still gain information here with our higher density.
With such a high density, how do you deal with the reference and the ground electrode? Where are they positioned?
The ground electrode is positioned accordingly where you want to position it, but we usually take the mastoid position here because of less electrical brain activity. And for referencing, it's very typical to use common average reference. Of course, you can also do different spatial filtering approaches afterwards, but we always use common average reference with our device.
Now we have the same problem as before. The questions are getting more and more instead of less and less. But in general, for the Pangolin system, if you're making your PhD, then I suggest select 3 papers that you like, assemble 1024 channels, replicate the data or the experiment, and the data that you get is brand new, much better spatial resolution, and your paper is actually done. Thank you very much, Leo. I hope we find the same doing your defense in 2 weeks.
Thank you, Christoph.